I didn't even know. That's good. How you doing, Professor?
I'm tired
Yeah.
after daylight savings. So.
Hey, just give us the tests and then class dismiss.
I can't do that.
You literally have that power.
I do have that power,
Yeah.
but I'm not going to use it.
Well, see,
Because there's a higher power than me that says I have to cover stuff in this class.
and there's an even higher power above that in which we don't say anything. No, I'm just messing. It's all good.
I came early too because we're interviewing new faculty for next year because we're hiring 2 new ones. So.
Oh, interesting.
Yeah.
Do you know for what? Is it for fill-ins for what is Milo RiceCon? Something like that?
No, I mean just our enrollment's been going up for the last few years since so.
Okay. So we just need more classes.
Yeah,
that makes sense.
Still alive.
Milo Rice is still 11.
I don't think I've met him.
Some would say, unfortunately, I'm not going to argue that I am some, but he is. What did I have him for?
For dynamics.
I think I had him for dynamics. I also think I had him for thermo.
Yeah.
Basically, I don't know about a third of real practical engineering. Honestly, probably half of all engineering because I had Milo Rice as a professor.
I see.
So I'm fully and legitimately lost. If Jerry as a human being didn't exist, I would have probably failed out of it. I have sat down so many times with that man, and he has explained what should be very basic concepts to me.
Yeah.
Like it's wild, but I'm here. We said it.
However, whatever gets the job done, right?
Yeah. You want to yourself? Nice to see you as well. How did tutoring go?
Somebody else showed up.
Crazy. Oh, also, second session of Pathfinder gonna happen tonight. Very excited.
Nice, nice.
See if the entire party dies. Hopefully not, but you know.
That's always the fun part, right?
Yeah, that is always the fun part.
Our DM is whenever we have a battle, like a combat encounter, our DM's like, I'm gonna try to kill you guys.
Yeah, yeah, that is in fact what we do every single time. It's always funny to me because I have very different players. One group that I run, they make me promise them solemnly that I will not pull a single punch. If a character is to die, I must let them die.
I see.
Which
That's
is
good.
very funny to me because usually you'd think like, oh, I want my character to live, and they're like, no, we build the characters powerful such that you have a hard time striking them down. If you get the chance to.
That's good. That's good. I think it's fun. It's fun on both sides. Then.
Yeah. Jerry, I'm assuming is probably finishing SI stuff.
Or probably on the way home.
That would be wild if he's going home because we have a D&D session.
I mean, the fact that he used to, or at least that he would leave, go watch a movie.
That is true. Yeah,
And
he
then
still
come
would
back.
come back. Yeah.
So-
All right,
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. It's a very different feel than what we're used to, right? We have sunlight today,
yes.
which is not what we're used to in this class. So how's everyone doing today?
All right.
Doing good, doing good. So yeah, probably everyone's noticed. So I did finish grading the midterms this afternoon. So the grades are on Canvas, and I brought them here with me today, so you guys can pick them up after class today, right? So the average on the midterm was 41 out of 50, which is exactly what it has been. I think this first midterm average has been right around there for like the last 3 years. So so you guys did good. So that was it was a good exam. And I've talked with a few of you, and I think everyone I think is surprised at just how much theoretical stuff and how much conceptual knowledge goes into this course. And it's really like nothing you've ever seen before. So I mean, the fact that you guys are taking on a lot of basically brand new information, basically a whole brand new way of thinking in terms of computational stuff, because before this, I don't think anyone's really had any computational courses. Is great. So you guys did really good on the exam overall. So you guys should be proud of yourselves. Okay, and so with that said, we're going to continue on with our lecture from last Monday. So it's been a while. So I'm going to do a little bit of review at the beginning of class today. Just to kind of remind you, we are talking about time marching schemes. So we're learning how to simulate unsteady problems. Okay. Another announcement, homework 4 is posted on Canvas. So homework 4 is available for you guys to look at. It is due not this Sunday, but the following Sunday, right? And so, we only have 4 more lectures until spring break. And so we have today, this week's lectures, next week's lectures, and then spring break. So I wanted to have the homework due right before spring break so that you guys can just turn it in and then just not worry about it over spring break while I'm grading this stuff, okay? So that's kind of what the due date is there for. And also I think we'll probably finish everything by next week as well, like when you the homework. Okay. But go ahead and take a look. I think after today you should be able to do a lot of it. And anything else, we'll learn as we go. Okay. All right. I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get going then. All right, so the theme for today is time marching scheme. Time marching schemes for unsteady problems. Okay. All right. So the whole theme of the next last week and this week is the fact that we're introducing a time derivative to our our usual convection diffusion equation. Okay? Time derivative is meant to represent the fact that we're now looking at situations that can change with time. All right, so basically we're now looking at introducing this term into our equation, okay? And just like we normally do, whenever we see a derivative in this class, we like to approximate it using a finite difference, right? And so for a time derivative like this, our finite difference approximation looks like the following. So if phi at n plus 1 minus phi at n, all divided by delta t. Okay. Notice how there's a few differences with this derivative than what we're normally used to. Okay. The first one, I think the most obvious one, is the fact that we're differencing now on the time index. Okay. Normally, when we use our finite difference, we normally put it on the subscript. But now that we're introducing time, we have to have a different index that's associated with it. Okay? So that's the superscript. And then the other difference here is, of course, delta t, which is no longer the grid sizing, but this is now the time step size. Okay? And so I think we discussed time step size a little bit last time, but let's give a little bit more context for the time step size. Because our solutions are changing with time now, when we view our results, we're going to view our results as an animation or video. Okay. And the time step size, you can think of it almost as the amount of time in between the frames of our animation. And so everything that you understand about how videos are, how videos work in terms of things like frames per second, resolution of videos, all of that knowledge can be used here. Okay. All right. Yes, question.
If we have some variable n that is supposed to be a time index, and we're assuming that like n is present, why would we want information from the future with n plus 1?
Yeah, no, it's a good question. So our mindset for this one's a little bit different as well, because for the space ones, we kind of request information from everywhere in the grid at once because it's in space. But when we're talking about time marching, we don't know what's happening in the future yet. And so actually, when we plug this into our equation, this thing, what you'll see is that we arrange it algebraically so that we actually solve for this n plus 1. And so the n plus 1 goes on one side of the equation, and we say that whatever's happening in the future is equal to this, where everything that's stuff that we know. Yeah, so the mindset changes a little bit, and that's why we call it time marching schemes rather than just straight up finite difference. Yeah. Mm-hmm. Okay. And so last Monday, we started using this for the first time, and we were applying it in kind of the simplest way, which is the explicit Euler way. So with explicit Euler, we basically took our usual equation and we plugged in finite differences for all the derivatives. Okay? So let me go ahead and plug in our usual equation here. So we have partial phi partial t is equal to, and this is in 1D, minus u, partial phi partial x plus k, partial squared phi, partial squared, plus q of x. Okay. For now, we're going to assume q of x is constant, as well as u and k. All right, so everything on the right side of this equal sign we've seen before. So this minus u partial phi partial x, this is our convection term. Okay. So it has a convection velocity as well as the first order derivative in space. Our second term there is our diffusion term because it's a second order derivative in space and it has our diffusion constant k. Right, and the q of x there is our source. Okay. And so what we did was that we took this equation and we replaced every derivative with a finite difference. Okay. being careful to know that, whether our derivative is in time versus our derivative in space, okay? And then we use different schemes depending on that. Okay, and so for the time derivative, I just wrote that up there. So, we can go ahead and plug that in there. So for partial phi partial t, we have phi n plus 1 at I minus phi at I n, all divided by delta t, okay, is equal to minus u times partial phi partial x. So remember, partial phi partial x is a derivative in space. And so we're going to plug in our usual space derivatives here. Okay. For now, I'm just going to assume that the solution is going to be stable. And so I'm just going to use a central difference here just for simplicity. I haven't established a direction for u. Yeah. Okay. And for the diffusion derivative, we have phi I plus 1 minus 2 phi I plus phi I minus 1, all divided by delta x squared, plus q at x I. All right. So that's just kind of our usual playbook here, right? So, whenever we see a derivative, we like to replace them with a finite difference. The only difference here is that, we have a time derivative now instead. Okay. All right. And so a key part of this whole endeavor is that, when we look at all the phi terms on the right-hand side here, okay, all the phi terms on the right-hand side there, they have their normal spatial index, right? And so they have their I plus 1, I minus 1s, I is just as usual. Okay? But in order for this to work within a time marching scheme, we also need to assign a time index as well. Okay? We have really two choices for a time index. We either have n plus 1 or n. Okay. And so before we can move on, we need to assign, either an n plus 1 or an n to all these phi terms. And so the simplest thing we can do is we can look at all the phi terms here and assign them either one or the other. Okay? There's different algorithms out there where you kind of mix and match. We're not really going to get into those. So those are kind of a little bit too, they take a little bit too long to develop. And so we're either going to go one or the other. Okay. And so for initially, we're starting with n. Okay. And so we're assigning a time index of n for all of the phi terms on the right-hand side. Okay, so this is the one that we're choosing. It's n right here. Okay. And so by doing that, by assigning a time value of n, this gives us the explicit Euler method, okay, with emphasis on explicit. Later today, we'll go over the implicit Euler, where we'll make the opposite choice, where we'll assign n plus 1, and we'll see how that affects our equations. Okay. So now that we've assigned a time index to all of those phi values, we're ready to solve this algebraically. Okay? And the way that these methods work is that, our unknown here is the n plus 1 term. Okay. And so what we're going to do is we're going to rearrange algebraically to solve for the n plus 1 term. which, if we did things correctly and we are properly using an explicit method, there should only be one n+1 term in the equation. All right, so we can look back at our equation here. Let me zoom out a bit so you can see it all. Okay. And so if we look at our equation here, we indeed only have one n+1 term, which is just the guy on the left. Okay. And so we need to kind of rearrange these things around. So I'm not going to go through that algebra again. We did that last Monday, but I'll just kind of give you the final result. But before we do that, are there any questions on this so far? All right, and so if we rearrange this algebraically, and I'm going to do kind of what we usually do too, where I group them like terms, we end up with the following. So b I n+1 is equal to, and I'm leaving everything in terms of variable, so you can just kind of plug into this expression later. So you have u delta t divided by 2 delta x plus k delta t divided by delta x squared b I minus 1 at n plus 1 minus 2k delta t divided by delta x squared ti at n, okay, plus minus u delta t divided by 2 delta x plus k delta t divided by delta x squared b I plus 1 and n plus q of x I delta t. The explicit or time okay. It looks scary. I know there's a lot going on there, but if you look at actually the amount of variables that are in there, it's not that many because a lot of variables kind of show up more than once. Okay, and the reason I do this is just to kind of group, because probably at this point what we're going to do is we're going to put that right hand side into a matrix form, and so when you put these equations in terms of the coefficients, it makes forming the matrices a lot easier. So this form of the equation right here is conducive to writing the code, which is what we're going to do. Okay. And so if you apply this method and if you apply it onto a one-dimensional grid, okay, and so we're going to apply it onto a 1D grid, and then what we're going to do also is we're going to put it in matrix form. In this case, it's going to be the right-hand side. We end up with the following. So we have phi I n plus 1 is equal to a phi I at n plus b. Okay. So this is kind of the symbolic form of what we're going to get. Okay, so this a right here, this is our coefficient matrix. This phi I at n, remember this is the solution at the current time step, which is known. And this B is just anything else. So any kind of boundary conditions or source terms, they're kind of added to it. Okay. Should be more specific. I was just going to call it extra stuff, but let's actually call it source plus boundary conditions. Okay. And so the benefit of this method right here, you can actually see it in this form right here. Okay. Because remember, what we're solving for is this guy, right? We actually want the solution at the next time step, which is unknown. Okay. So the equations that we're solving is going to be 4 for that. Okay. What's different about this situation, which is different from all the other situations that we've encountered, is the fact that our unknown here, or the thing that we want to solve for, is kind of by itself on one side of the equation, right? If you think about, all the other problems that we've solved before, usually the coefficient matrix is next to that, right? So we have the coefficient matrix multiplied by the thing that we want, which is the solution vector, is equal to something else, okay? But we don't have that here. We have our unknown, or we have our desired solution by itself on one side of the equation. Okay, this lets us explicitly solve for its value, without having to do any kind of matrix inversion. Okay, so that's where this method gets its name, because it gives you an explicit equation, an explicit relationship to solve for the unknown. And so for the first time ever in this class, we won't actually be solving a linear system of equations. We're actually just going to be doing matrix vector multiplication, which is supremely cheap. It's so cheap compared to solving a linear system. Okay, and so I think we left off basically right here on Monday. And so I was just kind of right on the cusp of showing you the code. But are there any questions on this before we jump into the code? Okay. All right. So what we did on Monday was we did kind of a worked example. Okay. And we basically solved for the coefficients of that matrix. Okay? I never showed you its implementation in the code. So let me go ahead and do that. So let me go ahead and share my screen here. Okay. And so if you look back in your notes, you'll see you'll see me solve for these coefficients here. Okay. I'm not going to go through that again just for the sake of time, because I want to move on to implicit stuff today. But I want to show you how this actually works. Okay? Let's just ignore this for now. That's going to be for a second. Okay. And I believe someone asked me last week if, is this going to end up being a loop? And it is, right? And so the loop looks exactly like this. And so basically, what we're going to do is we're going to loop over the time step. Okay, so instead of looping over the space domain, we're going to loop over the time domain, and we're going to solve from time step 1 until time step nt, where nt here, nt is the number of time steps that we want to solve. Okay? So just like in the space domain where we have n, or nx or ny, we also have nt, which is the number of time steps. Okay, and so the main action of the equation is actually right here. And so what this equation is basically saying is that sol next, and so sol next is equal to b at n+1. Okay. Right. What that's equal to is the coefficient matrix A multiplied by sol current, and sol current is phi at n, plus our source terms and our boundary conditions. Okay. So it's strictly just a matrix vector multiplication. Okay, so there's none of this involved, right? And so if you looked at all your previous codes, we had this kind of backslash operator. Okay, we don't have that here. We have just straight up matrix vector multiplication. Okay, and then what I do from here, this kind of extra step here, is the fact that once we solve for sol next, then that now becomes the current solution. And so that's all that this says. And so it's basically saying sol current is now equal to sol next. And then we're going to plot it. Okay. So this plot that's going to come up is going to look a little bit weird. And so the way it works is that I don't have a video here, but I've basically taken a screenshot of the solution at different points in time. Okay. So what you're going to see is basically a plot that has a bunch of lines on it, where each line represents the solution at a different time. Okay. So think of like, if someone's doing a jumping jack and you took like a snapshot every, 0.1 seconds or something, and you overlaid them all together, right? It's going to look like the guys like Cthulhu or something with like a ton of arms, but you kind of understand what it is, right? And so it's just kind of an in motion picture. It's in motion, it's just a static image of that. Okay. Okay, so let's look and see what happens when we just kind of run this code as it is. Okay, so here's our solution. So it's a little bit hard to see, but if you kind of look zoomed in right here, you can see there's a lot of different solutions there. Okay, but obviously that's not the thing that stands out. So the thing that stands out is this kind of zigzag looking thing, right? And what should stand out even more here is this magnitude. Okay, and so the magnitude of this peak is approximately 5 times 10 to the 27. Right? That's really, really high. And so we're really pushing on the borders of what we can do. Okay. So this is wrong. Okay, so this is not what the solution should look like. And so if you look at our example, it's just a very simple unsteady diffusion. And so there's no way we can get this kind of height. Okay. But this plot should remind you of something else, right? And so if we look at this plot, we can see that we start at 0, and then we go to some very negative number, and then we shoot up to some very high positive number, and then we shoot down to a negative number, and then we shoot back up to a positive number, right? So this looks like oscillations. In particular, this looks like unbounded oscillations, right? And so this looks very similar to when we covered convection, and we ended up with an unsteady solution, except this is kind of an unstable solution. Written in serial killer handwriting. Okay. And so if you remember from convection, when you had an unstable solution, it was characterized by these unbounded oscillations. Okay. And so that's kind of the caveat with explicit Euler. So with explicit Euler, yes, it's very simple. Yes, it's very fast compared to what we're going to be doing, but you run the risk of having an unstable solution. Okay. All right. And so what can you do in this situation? And so the good thing is for an unstable solution, there's a way that we can fix it, right? And so if you think back to how we fixed instability in convection, all we did was that we reduced the grid size, right? So we made delta X smaller. And what we saw was that if we made delta X small enough, the Peclet number was below 2, and we ended up with a stable solution. Okay? Here it's very similar, right? There's no such Peclet number for unsteady problems, unfortunately, but we can use the same kind of logic, right? And so what we're going to do is we're going to make delta T smaller. Okay. And so the kind of the logic is that if you make delta T smaller, you make the time step size smaller, it should stabilize the solution. Okay. Okay. And so let's see what that looks like. So I'm going to close this plot. Okay. And let me uncomment this. Okay. All right. And so the coefficients in the matrix before we made the time step smaller, look like this, right? And so let's reduce that time step size. And so instead of 0.1, which is what we use for this upper matrix, let's reduce the time step size to 0.01. Okay, so we basically reduce the time step size by a factor of 10. Okay. And so what that's going to do is that it's going to change the coefficients of the matrix. And so you can verify this, of course. So you can plug in kind of the smaller delta T. You can go back in your notes and see and just verify that these are the correct values. Okay. And so I'm going to run the same code except with these smaller coefficients here. Okay. So I'm going to come down here. Instead of A, I'm going to multiply by A fine. So fine is the fact that we refine the time step size. Okay. Everything else is the same. So the boundary conditions are exactly the same. the coefficients, I mean, the diffusion constant is all the same. So the only thing we changed was just the time step size. Okay? So let me go ahead and run this solution now. And you can see now that we have a stable solution, right? And so it's a little bit hard to read, but you know, what we're basically doing. And so the way to kind of read this is that we're starting at this solution. So this is the solution at time is equal to 0. Okay. And then as time progresses, you know, we kind of converge onto a steady state. Okay. So the final solution here, I don't know why I tried to do that, but the final solution is this kind of top purple one right here, where we start down here, and then each time frame, each time step, we kind of inch closer and closer to the steady state solution, which is up here. Okay, and so in other words, you know, we fixed our instability problem by lowering the time step size. Any questions on that? All right, so explicit, you were very good. You know, it's you know, explicit methods are used, you know, all over the world in different codes, but you know, you always have to be careful about instability. Okay. All right. And so let me go back to the written notes here. Okay, so we're back here. And so explicit methods. Explicit methods can be cheap. Since there is no algebraic solve. But right, so that's always something you have to watch out for when you're using explicit methods. Okay. And in fact, you know, this problem with instability is so big that sometimes, a lot of times, it actually cancels out kind of the cheapness of the situation. Okay. Because a lot of times, you know, when you have an unsteady simulation, you want to run it until you reach a simulation time of X, right? So maybe you want to run it for like 3 seconds. So you want to simulate 3 seconds of your simulation. Okay. What happens when you reduce the time step size is that you have to run more time steps in order to get a converged solution. So that's N and T. Okay. And so in our example that we just did, you know, we reduced the time step size by a factor of 10. Okay. But in order to simulate the exact same amount of time, that means we'd have to jack up NT by a factor of 10 as well. Okay. And so sometimes that could actually lead you to an increase in cost. Okay. And so explicit methods, there's always this kind of dance between what should I set the time step size to, and is this going to be a stable solution? All right. But just like convection, you know, we can actually change our algorithm a little bit. We can change our scheme a little bit to make sure that we're always stable, right? And so, that's what we're going to do next. And so the next method that we're going to learn is called implicit Euler. So the idea behind implicit Euler is that we're going to change our scheme a little bit. We're going to change our strategy to basically make sure that we're always stable. Okay? Okay. So just like before, let's start with our original equation. So we have partial t is equal to minus u partial phi partial x plus k partial squared phi partial x squared plus q of x I. Okay. So that's our starting equation. That's our unsteady convection diffusion equation. Okay. We're starting from the same point, so we haven't applied our change of strategy yet. All right, so just like before, we're going to apply finite difference here. Okay, so all the derivatives we're going to replace with the finite difference. So we'll start with the time derivative. We have the convection derivative, which again, I'm going to assume is central difference. Just for simplicity. And then we have our source term. Okay. So far, all the same. And so, it's just our usual playbook. We see derivative, we apply finite difference. Okay. Where this is going to be different and how this scheme is different is what we do from here. Okay. And so just like we saw with the explicit schemes, okay, if we look at all the phi terms on this side of the equation, none of them have a time index associated with it. Okay, so we need to assign that. And so we have two options. So it's either n plus 1 or n to all phi. So last time we were at this point, we selected n. Okay, so we applied a time step of n for all the phi terms here, and that led us to the explicit Euler. Now we're going to apply n plus 1 to all those terms. Okay, so we have n plus 1, n plus 1, n plus 1, n plus 1, n plus 1. All right, so this changes our algebra, a bit, okay? Because what we're gonna do next is, we are still gonna use algebra. And so, we're gonna move all the terms with n plus 1 to the left-hand side, and all the terms with n, we're gonna move to the right. Okay? Also going to multiply by delta t just because, just kind of clean that up. Okay. And so let's see what happens. So now our left-hand side is going to be a lot more crowded than it was before. Remember before for explicit viewer, we only had one term on the left-hand side, which is just b at I n plus 1. Now we have a lot more in implicit viewer. Okay. Okay, and so if we do that, we have b I n plus 1. So this is kind of the leftover from the time derivative. Okay. Then we have the convection term. So we have u delta t divided by 2 delta x times b I plus 1 and plus 1 minus b I minus 1 and plus 1. Okay. And then the diffusion term. So we have minus k delta t divided by delta x squared b I plus 1 and plus 1 minus b I and plus 1 plus b I minus 1 and plus 1. Okay. And on the right-hand side, we have b I at n plus q of xi times delta t. It's a lot of indices, I know. So not only a subscript, but now you have a superscript to keep track of, right? But believe it or not, this is not hell yet, right? We're not in hell just yet, because then after this we're going to do 2D problems. So we have I, j with a bunch of plus 1 minus 1s, then with the n plus 1 as well. So that's when it really becomes hell. And so, just want to prep you guys before we get there. Okay. All right, so we're almost there. And so I'm going to do one more step here before we kind of box this equation. And so on the left-hand side, I'm going to combine the like terms in terms of phi. Okay. This here, we're going to combine. We're going to combine like terms for phi. And then we end up with our boxed equation. So what we end up with is minus u of phi divided by 2 delta x plus a delta t divided by delta x squared times b I minus 1 and plus 1. Okay, so that's the I minus 1 term plus 1 plus 2k delta t divided by delta x squared bi n plus 1 plus u delta t divided by 2 delta x minus k delta t over delta x squared bi plus 1 n plus 1. Okay. bin plus q xi. So we can put a box around this one. Okay. So this right here is implicit 1D convection diffusion. So again, I know it's a lot. It's a lot of stuff. Oh, question, yes.
For the opposite one, the Q of X, it was just X, and this one's X sub I. Is there a difference?
I must have forgot the X sub I from before. Yeah, because remember we're applying this on a grid. So then the X, whenever you see X, you have to substitute X sub I. Yeah, good catch. So it's a lot, but you remember a lot of these variables here are repeated. So you'll see K there, K shows up, I think like 3 times, delta X shows up like 5 times, delta T like 4 times. And so, you're plugging in, it's a lot of stuff, but you're plugging in the same variable kind of over and over. All right, any questions for how we got up to this point here?
What's the second term in the VI amplifier?
This is 2K delta T divided by delta X squared. Let me rewrite it so it's a bit more clear. It's 2K delta T. Yeah. Is that the term you're talking about?
Or the one. Plus 2K delta T.
Yeah, the one comes from this guy right here.
Oh.
Yeah. One comes from the time derivative. Yeah. Yeah, it looks weird. Yeah, it looks weird to have just a random one kind of floating around there, but yeah, that's how it's supposed to be. Any other questions on how we obtain this guy here? Okay. All right. So before we jump into an example, I do want to point out kind of an important feature of this. Okay. And so remember before we had this kind of situation with VI n plus 1 is equal to A VI n plus B. Okay. Right, so that's the situation we had for explicit order, right, or explicit U. And so to solve for the solution at the next time step, all you had to do was take your coefficient matrix, multiply it by the current solution, and then add B to it, right? And so it's very, very straightforward, right? So matrix vector multiplication. Here we don't have that because if you look at the left-hand side of the equation, we have all these coefficients here, right? And so now our coefficient matrix is not here, right? So it's not next to phi n. Our coefficient matrix is here on this side. Okay. Right, so all the terms I've underlined in red, those essentially become the coefficients of a matrix, right? So very, very much in the same way that we did from, in steady problems. And so that means, so since our coefficient matrix is on the left-hand side, and always the way that we formulate these equations, the thing that we want to solve for, or the unknown, is also on the left-hand side, okay? And so the only way to kind of solve for phi n plus 1 is to basically invert this matrix, right? So we're going to multiply with A inverse, or in other words, we're going to solve a system of linear algebraic equations. Okay? And so we're kind of back to our usual method, right? And so our usual method for solving this problem is just to solve a system of linear equations. In other words, to invert a matrix. Okay. The only difference here is that because it's unsteady, we're going to keep doing this, right? So we're going to put this matrix inversion inside a loop. And so we're solving not just once, but we're solving the system of equations multiple times. Okay. And so the cost adds up a lot. And so if you think back to homework 2, right? Homework 2, remember I had you do the problem where, I gave you a 2D code and I had you time how long it takes the code based on how big your grid is, right? Now imagine that code, but you're multiplying it by 1,000 because you're solving for 1,000 time steps, right? And so even for a fairly, what you may think is a fairly cheap simulation. So let's say you had a good computer and you're able to do the 100 by 100 grid in about a minute. Okay. And so if you can do the 100 by 100 grid in a minute, but you do that 1,000 times, right? Now all of a sudden you're waiting 1,000 minutes for your solution. Right? So that's like a thing where like you hit go, you go to sleep, you pray before you go to sleep that your simulation is going to work and it's not going to fail. You wake up and then you hope that's there. If it's not, then you cry. So, and so that's the thing with implicit viewer is that you don't have to worry about, we no longer have to worry about instability, but you have to really kind of have a lot of faith in how you code stuff because there really can be nothing else wrong. Otherwise, you're going to be sitting and waiting for an hour and only for your solution to fail. We're not going to do any kind of problems like that for now, right? For your final project, you will be, but we're going to do much more modest problems for now. Okay, so no crying yet. All right, any questions on this? Okay, so let's see it. Let's put some numbers on this. So let's see what it actually looks like in an example. Okay, so let's do the same problem that we did before for the explicit Euler. Let's solve it with implicit Euler instead. Okay, so we have partial phi, partial t is equal to 3 partial squared phi, partial x squared. Okay. For the boundary conditions, we have Dirichlet boundary condition on the left-hand side. So we have phi at x is equal to 0 and t is equal to 1. And then the partial phi, partial x at x is equal to 1 and all times is equal to 2. Okay. And so for our initial condition, we're going to have all 0. So phi at all values of x, and t is equal to 0, is equal to 0. Okay, so we're going to start with a 0 initialization, just like we know. Okay. Okay. And so what we want to do is we want to solve this with implicit Euler, or implicit Euler. We're going to assume a grid, we're going to assume a spatial grid of 5 points. Our spatial grid is going to look like this. We have node 1, node 5, 3, 2, 4. Okay. And so if we have 5 points, and we know that on the left-hand side, we have x is equal to 0, on the right-hand side, we have x is equal to 1. That means our delta x, our grid spacing, which is assumed to be uniform throughout, is 0, 5. Okay. Our time step size, let's assume that is 0.1 seconds. And so this is going to be the same as our explicit Euler. Okay. As for the other variables, we can see from this equation here that our k, remember our k is our diffusion constant. And so it's just whatever value is in front of the second order derivative. Our k here is 3. Okay. And our u, which is our convection velocity, is 0 because we don't have any convection in this problem. Okay. But now that we have all of these variables, and so let me add delta x here. Okay. We have our 4 values here. So we have delta t, delta x, k, and u. We can now plug this into this above equation up here for implicit u, right? Remember, I said it looks scary, but it's literally just four things, and we're just plugging it over and over. Okay. Okay, and so if we do that, we get the following. So we get minus 4.8, EI minus 1, and plus 1, plus 10.6, and plus 1, minus 4.8, I plus 1, and plus 1 is equal to I at n. Okay. And in this problem, we don't have any source term, right? So there's no extra term there. So everything is just okay. So this is our kind of our time marching equation. So let's start applying this. In particular, let's apply this to all the interior nodes. Okay, so nodes 2, 3, and 4. We have I is equal to 2, I is equal to 3, I is equal to 4. Okay. All right, so at I is equal to 2, we have minus 4.8. B at I minus 1 here is V1, n plus 1, plus 10.6. BI, so it's V2, n plus 1, minus 4.8. V3, n plus 1 is equal to V2 at n. Okay. Then I'm going to repeat that for nodes 3 and 4. Okay. So this is our usual playbook, right? So we do all this finite difference, we apply it for all the interior nodes, and we get an equation for each interior node. Okay. Of course, that's not all the nodes, right? So we have 5 nodes in the system. So we have 3 equations. We're missing the end nodes. We have node 1 and node 5. Okay. But just like we normally do in these situations, whenever we have the end nodes, we have the nodes that are on the boundaries, we apply our boundary conditions. Okay. And our boundary conditions are going to give us our equations. So, if we look at our boundary conditions here, on the left-hand side at P1, we have a Dirichlet boundary condition. Okay. P1 is equal to 1. Okay. And at I is equal to 5, we have a Neumann boundary condition. So P5 minus P4 divided by delta x equal to 2 in this case. So in red there, I have our usual boundary conditions. And so, you can do what we usually do for I is equal to 5. You can take that delta x and move it to the other side of the equation. So I'll probably do that in a second. But, I just want to kind of illustrate that, the boundary condition equations. Okay. All right. And keeping along with the theme of time marching, we have to assign a time index to each of these boundary conditions as well. Okay. And so keeping with the theme for implicit, for all of the phi terms, let's apply them at n plus 1. And so we're going to apply n plus 1 to all phi terms. Okay. All right, so we're basically done. And so now that we have it in this form, let's go ahead and put it in matrix form, because we love matrices in this class. I love matrices in class. You don't have to love matrices. Okay, so matrix form. So this is very much like we would normally do. Actually, I think implicit Euler is actually more similar to everything we've done up to this point, more so than explicit. Explicit is kind of the weird one, but chronologically you have to cover explicit first. All right, so our matrix form looks like the following. So we have 1, 0, 0, 0, 0. Let's multiply by P1, P2, P3, P4, P5, and plus 1. Okay. We have minus 4.8, 10.6, minus 4.8, 0, 0. Right-hand side, we have 1, E2 and N, P and N, P4 and N, and then 2 times delta X. All right, and so we get a system that that looks very similar to what we know, right? So we have a left-hand side matrix, we have our solution vector that we want to solve for, and we have a right-hand side vector where the right-hand side vector has everything that's known. So everything in the right should be known. Okay. And so to solve for this, we have to do it our usual way. And so to solve for phi n plus 1, we have to solve a linear system. So we have to invert a matrix, okay? Which is a lot more expensive. Okay? The difference here, and the reason why we're in implicit Euler is that we have to do this multiple times. And so I'm going to show you the code for this. Okay? And what you'll see is that we're going to have an outer loop, and so the outer loop is going to be over time, and within that loop we're going to have our usual MATLAB backslash. Okay. Right. Any questions on this? What is fee Y? Oh, that is just my poor handwriting. So that's fee 4. Excuse me. Fee 4. Yeah. Mhm. Any other questions on this before we jump in the code? Okay. And so remember, the time step size we used for this was 0.1. Okay? And if you recall from our initial explicit Euler example, our explicit Euler was unstable with delta t is equal to 0.1. Okay. Let's see what happens when we use implicit Euler with the exact same time step size. Okay. Okay, so let me go ahead and switch over to MATLAB here. Right. And so the code that I want, this one. Yes, okay. All right, so the structure of this code looks very similar. So I have, what I've done here is I've defined the coefficient matrix, and so you should see matrix A is equal to zeros. And I'm assigning the values of the matrix, according to this assignment operation. And so we have 1s, minus 4.8, 10.6. So, very much the same as what we have in the notes. Okay. All right, and when we come to the main loop, this is kind of what it looks like, right? So we're looping over time, just like we normally do. And this is the main thing that we have here. So our solution next is equal to A backslash B. Okay. We no longer can do just matrix vector multiplication because we have to solve a linear system. Okay. Okay. The other thing that we have here is, we're assigning the values for the vector B. Okay. And so if you recall, from the example that we worked out, entries 2, 3, and 4 of the right-hand side vector contain the current solution. Okay. And so that's all I'm doing here. And so basically I'm assigning the current solution values to the right-hand side vector. Okay. Remember, the current solution is going to update every time step. Okay. And then after we do that, we solve our linear system, we update our current solution, and then we're going to plot. Okay. And so the plot for this is going to look the same as before, except it's going to be stable. Okay. All right. So let me go ahead and run this code. Right. And so what you should see here is that even with the time step size of 0.1, right? We end up with a stable solution, right? And so we start out with the kind of the blue curve on the bottom, and eventually we convert to this straight line right here. Okay. And if you recall from explicit Euler, we ended up with 5 times 10 to the 27th power, right, for 0.1. We don't have that here for implicit. Okay? So this is the benefit of implicit methods, that you almost always you end up with a stable solution. Okay? There are ways to get an unstable solution with implicit, but you have to actually be trying to break the code. Right? So as long as you're not trying to break the code, for implicit, you're going to be okay. The thing that you're not seeing, and we're not really seeing it in this case because it's a pretty simple case, is that the cost per time step for implicit methods is a lot higher because we're doing this matrix inversion versus just a matrix vector multiplication. Okay. So those are your two kind of weapons here, right? So those are your two options for doing time marching. So you can do an explicit method where, on a per time step basis, it's going to be very fast because you're just doing matrix vector multiplication, but you run the risk of being unstable. Okay, so that's one way that you can solve these problems. Another way you can solve these problems is implicit, where you're guaranteed to be stable, but on a per time step basis, it's going to be a lot longer. Okay, and I kid you not. So once if you kind of want to see where this is going, so for the final project for this class, I'm going to have you implement an implicit 2D equation. Okay. It's not uncommon, it depends on how good your computer is, but it's not uncommon for that code to take around, 1 hour to 75 minutes to run. Okay, so if you can imagine, doing your final project, a lot of it is going to be sitting and waiting for the code to run. And so, these get expensive very quickly. And so, you don't see it here because it's a 1D case, but the cost can get pretty extreme. Okay. Luckily, if you set things up right, and if you kind of follow my recommendations when we get to the final project, you're hopefully only going to run the 1 hour code maybe like once or twice. basically don't do your testing on a fine. That's what we'll see. All right, any final questions on this? Okay, so I wanted to end class a little bit early just because I have the exams, and so you guys can come pick it up. If you have any other questions, you can always come see. But on Wednesday, when we come back, we'll see how this applies in 2D. Okay, so we're going to do 2D unsteady problems, and that'll really be in-depth. Okay, so thank you guys for coming today. Hope you guys enjoy the rest of your day. Hope you guys enjoy some sunlight that we now have, right? And I'll see you guys on Wednesday. Yeah. Oh, take a look at your exam. So make sure I added up all the points correctly. Make sure you read the feedback that I give you. And if you have any questions on it, just come and ask me. Okay.
You guys have fun.
If we're having to do like an implicit 2D equation with all of that, it has to be directly related to transfer, right?
Yes.
Okay.
Yeah.
Because I actually, it's more of a physics thing, but I actually do think, funnily enough, I came up with an equation that relates to this all.
Okay.
Funny.
Nice.
Yeah.
Yeah. Usually for this class, it's a set final project, so it's not like 410 where I'd actually explore. But I'm open to the idea. I think one time in the past I just kind of work on its own. We can discuss it once we get close. Yeah.
Two points in this one. How'd you know you didn't say that? You just read it quickly.
I read it very quickly.
Oh, okay. Check that out. That's kind of-
Yeah. So Zoom people, I'll bring the exam again on Wednesday. So if you want to come pick it up Wednesday, you can. Or you can just come to my office at any time. I'll have the.
Professor, I have a question.
Yeah.
How long do you keep the exams for?
How long do I keep them for?
Yeah.
I am required to keep them for a year.
Okay, so let's say last semester I didn't take up any of my exams for Computational.
It should be in my office. I throw them all into a drawer. So if you want, you can come to my office sometime and dig
Okay,
through the
cool.
file.
Yeah, every single time you pass it back, I wouldn't be in class. I just
Yeah.
never got any of my practice.
I
It's not
see,
even
I
about my
see.
class, people
Do you?
No, people have.
Okay.
Yeah, if you want to come by anytime, just anytime. It's all in a drawer, so it's going to be with all the exams that were not picked up, which was a lot last semester actually.
Really?
So
Oh, shoot, okay.
a ton of people didn't pick up their exams this semester. So yeah.
About homework.
Yeah.
three.
Uh-huh.
This is the solution is to -10.
Yep.
No matter how I try to.
Okay. I would probably need to look at your code. Yeah, so for the homework, I just graded it really quickly. I mean, I just released the completion.
I did it a little bit different.
Yeah.
But it was just like the convection negative.
Okay. Yeah, I'll take a look at your code. Just send me an email to remind me. Okay. Yep.
I was just curious if the point I lost on this problem was because I.
Yes.
Okay.
Yep.
Thank you.
I think I followed the arrow. Sample all that. The last one, right? Oh, yeah, how do I substitute again?